like I'm dreaming. When that blood goes rattling through my veins, my ears start to ring. I've noticed what matters, and I got nothing to lose but darkness and shadows. Got nothing.
So here's my project in real life. This is what it looks like. Pretty much basically what it looks like in the drawings. See, we got a base right here. This is what it looks like in the drawings. Try to focus most of the wood to this side over here, because you don't want wood where your ball's gonna be dropping around here, because that would interfere with where the ball is dropping. Now we have each of these set up exactly 3.5 inches apart to hold this exactly in place. We did this on both sides to hold this in, so this doesn't move at all. So that works really well. Then what we also did is we put this together by using a basketball, and we put this in, and each of these are 1 foot by 1/2, holding a basketball perfectly in the middle, right here. Okay, hinge here, 1 hinge right there. Basically what happens is when you pull this string, that pulls that down, the ball drops. Now if you look over here, after the ball drops, the video camera will be sitting right about here, so it can see all the numbers which are written here and where the ball is dropping. Now I can also, if the video camera was not able to be far enough away, I can move this so that the ball drops closer to the numbers, and that makes it easier to read, giving us better results. Now, each of these numbers is marked at exactly the right amount of inches from the ground up. So what we were measuring is the rebound of the ball, which is the generated force from here dropping, picking up gravity, and dropping, compressing into the ground. And then the more it compresses, the more it bounces up. So I think our highest rebound was around 48, which is 4 feet right here. And so that's about this height. And it goes right to here. And if you look, we got 5 feet all the way down. Nothing bounced up to 5 feet, so we didn't have to worry about that as much. But our drop points are 6 feet, 5 feet, 4 feet, 3 feet, 2 feet. Each of those will help me measure the different compressive force, and in the end, how it affects the rebound of the ball. After I had the project built, I continued on testing it. For each time I dropped the ball, the camera would be recording the rebound height. Later, I would revisit the information and record it into my science fair notebook. Once recorded in my science fair notebook, all of the information was then transferred into graph. Here's the drop from 6 feet, 5 feet, 4 feet, 3 feet, and 2 feet. After the graphs were recorded, I found the averages for each drop and then recorded them into their own separate graph, showing the differences between each drop's rebound. In my experiment, I dropped the ball from 6 feet, 5 feet, 4 feet, 3 feet, and 2 feet to simulate a ball dropping and compressing and then rebounding. The ball is placed on a trapdoor that is held up by a sliding lock. When the sliding lock is pulled, the trapdoor is released and the ball falls because of gravity. When the ball comes into contact with the ground, it is going a certain speed. The longer the ball is dropped, the more speed it accumulates. When the ball is dropped from a high area, there is more speed forcing it to the ground. When it is dropped from smaller areas, the less speed forcing it to the ground. The amount of force pushing a ball towards the ground will affect the amount of compression created. Compression is a force or pressure that attempts to flatten or squeeze a material. In this case, it is gravity, forcing the ball to compress. The act of compressing is then followed by the act of the object trying to retain its original shape, which would have pushed away from the ground to cause the ball to rebound. The longer the ball falls, the more speed it accumulates. The more speed forcing it to the ground, the more it compresses, and the more compression that is created by the speed from the gravity, the higher the rebound. When the rebound reaches its apex is where my camera will capture the height at which the bottom of the ball reaches its maximum height. In all of my graphs, it seems that there is very little uncertainty in the results, telling me that the machine was built well so that the ball was dropped the right way every time, creating similar results and less difference between the results. As you see in my graphs, the results are very close to each other, all within 1.7 inches of each other. When the ball was dropped from the highest level of the tower, which was 6 feet, it rebounded the highest, reaching the highest point of 48 inches. When the basketball was dropped from the lowest point of the tower, 2 feet, it bounced the lowest, achieving the lowest height of 20.8 inches. This proved my hypothesis that the ball that is dropped from the highest point will rebound the highest because there is more pressure being put on the ball when it hits the ground, forcing it to compress more. The ball that is dropped from the lowest point will rebound the lowest because there is less pressure being put on the ball. It hits the ground, forcing it to compress less and bounce lower. During the building of my project, I encountered many problems. My design had faults in the beginning. I must have redone it 5 times before I found a design that worked. So just as a suggestion, find a design that will work before you start building. Once I got working, I was not able to use the power saw so that I could make clean cuts. Thinking I was solving the problem by using a handsaw, I was actually creating more of a problem. When I began to put everything together, having the wood cut differently than it should have been did not help and made it hard to balance it on its platform. Once that problem was solved, the trapdoor failed to open properly and was lopsided. Then I had to rebuild the whole trapdoor and replace it on a different piece of wood. After that, the sliding lock was not staying in place, making it hard for the door to open fully. So I just screwed on the opposite side. Once this was all accomplished, the project worked perfectly and the tests were all taken. Before you start building, make sure you have power tools and all the wood that you need, and most of all, have an organized plan on what you're going to do. If you have acquired all of these, then you can start building your project. And just remember that every problem has a solution, so don't panic when something doesn't go as planned. I recommend this project to anyone so that they can learn more about science in general, plus the added bonus about learning about gravity and compressive forces, and how the two together affect the way the ball rebounds. And now for my acknowledgments. Thank you, Scott Brown, for helping me build and buying supplies. Thank you, Barbara Brown, for driving me around to get my work done. Thank you, James Brown, for giving me advice on how to construct the project. Thank you, Ryan Brown, for holding my screwdriver once. Thank you, Scott Nelson, for giving me advice on how to construct the project. Thank you, Mark Sturts, for giving me advice on how to construct the project. Thank you, Scott Harden, for bothering me while I was doing my work. Thank you, Tina Mongi, for giving me advice on how to construct the project. And a special thanks to Mr. Ozeni, the best science teacher ever, for supporting our whole class throughout this project and making it possible for all of us to get this done. And another special thanks to Mr. Snedden for also supporting our class, helping us to get this done. How do I turn this off? Oh yeah.